So in this section, we're going to talk about how to integrate in order to get antiderivatives involving our inverse trig functions. So just to recall from 5.6, for example, the derivative of arcsine of x is 1 over the square root of 1 minus x squared. So we're just going to work backwards in that the antiderivative then of 1 over the square root of 1 minus x squared will be our arcsine of x plus possibly a constant. The one minor difference, as you see at the bottom of the screen now, is the way the rule is written with regards to the constant in our square root, for example, the a squared piece. This is a more general rule, and this is just saying that, if you have the general form 1 over the square root of some constant squared minus x squared, the rule is always going to boil down to arcsine, still going to be an arcsine, but how that constant a squared affects it is that the inside of our arcsine, we're going to have x divided by a plus c. And so this is just a more general rule, and it's just saying that it's still going to end up being an arcsine. It's still going to be an arcsine, whether that's a 1 in front or a constant in front. So to derive this, I just want to do this one time. This is more for a proof, so you can just follow along. Is how did they know that? Well, if you wanted that front term to be a 1 so that it matched our rule exactly, here's what you would have to do algebraically. You'd have to say, okay, if that front term is going to be 1, I have to factor out the a squared, so then I'm left with 1 minus an x squared over an a squared inside my square root. And if that's the case, I'm going to do a couple things here. I then have two things being multiplied together inside my square root. And so I could take the square root of both of them separately. And while I'm doing this, x squared over a squared, you could think of this as x divided by a quantity squared. Just note that x over a times x over a is still x squared over a squared. And so the square root of a squared, that's just a. So that's a constant of 1 over a that gets pulled out front. And I'm now left with this square root of, with the 1 in front, which is what I really wanted, minus x over a squared. Well, the good news is I got my 1 in front. The bad news now is I don't have just x squared inside my square root. I have an x over a squared. So I would have to do u substitution. And my u would be x over a. And then as a result, remember that a is a constant. The derivative then would be 1 over a dx. And what's nice is when I do my substitution now, I get my 1 over the square root of 1 minus u squared. And then what's left over? Well, notice I still have a 1 over a and a dx left, which is exactly what du is. And that rule right there is exactly the derivative of arcsine of, well, in this case, u. So this would be arcsine of u plus c. And last but not least, when I turn it back, what did u equal? U was just the x over a. So I do get still arcsine of x over a. Okay, just like we had on the last screen. Now, obviously, anytime we have a constant like that in front, we don't want to have to do all of this algebra every single time because there's a nice pattern here, and that's what this is really indicating is that, hey, even if that number in front is not a 1, the pattern, it's still going to be an arcsine, but it's going to be an x divided by a every single time. And so these are the rules that we're going to have memorized. All right, so for the top one here, that's one we've been working on. It's going to be arcsine of just x divided by a plus c. The middle one looks just like arctangent, except again, instead of a 1 in front, it could be any constant, that's fine. As a result, it's still going to be an arctangent, but to account for that first constant being something other than 1, there's going to be a 1 over a in front, and then arctangent of x over a plus c. And lastly, this is going to look like arcsecant. It's okay, there's no absolute values on that x in front. It's going to show up in our antiderivative rule, but this is going to be 1 over a arcsecant of absolute value of x over a plus c. So these are going to be the three rules, the three antiderivative rules that you're going to be using in this course. And the one thing I want to note in blue that I could make is we had 6 derivative rules, but there are no rules in here for arc cosine, arc cotangent, or arc cosecant. Why is that? Well, if I were to give you this antiderivative here, negative 1 over the square root of 1 minus x squared, and you were to say, or ask yourself, the derivative of what gives you negative 1 over the square root of 1 minus x squared, you could very well say, hey, that's arc cosine. And you would be 100% right. But what that's also equal to, that is also equal to the negative arc sine of x, right? Because that negative could just be pulled out front like a constant. 1 over the square root of 1 minus x squared gives me an arc sine. And so it has the same it'll have the same derivative as negative arc sine of x. And go ahead and check it. If you take the derivative of arc cosine of x, or you take the derivative of negative arc sine of x, since they have the same derivative, they just differ by a negative, both of those are going to equal negative 1 over the square root of 1 minus x squared. So to reduce the number of rules we have to memorize, since they're all going to be equal, we only have 3 antiderivative rules for the positive derivative rules, thinking that if any of them are negative, we can just pull that negative out front and treat it like we would any general constant. All right, so on this one here, first I would ask you to identify which of the inverse trig functions is this going to be, if it's going to be one, because it may not be, it could be something else. And this looks very much like arc sine. In this case here, remember, this is my a squared piece. So if a squared is 9, then in my rule, a will be 3, and then there's my x squared. So arc sine says it's going to be just arc sine, it has no number in front, of x over a plus c. And that would be our antiderivative for that one there. This one, similar thing. One, I would identify that it looks very much like arctangent, where this is my a squared. Now, this would have to be my x squared, or at least my variable squared. So it's going to need u substitution. And for right now, you need to think that this is 2x quantity squared. You'd have to ask yourself, what am I squaring to get 4x squared? I'm squaring 2x squared. So if I were to rewrite this, just to emphasize that a little bit more, I could think of this as the square root of 3 squared plus 2x squared. So the arctangent rule, if you were to look back at it, had a squared plus x squared. So in here, a is going to be the square root of 3, and for our function piece, we're going to need u substitution, and u will be 2x, so that I get a squared plus a variable squared. We still have a dx there. So let's run through our substitution. So I still have 1 over, I'll keep writing it as the square root of 3 squared. I now have plus u squared in the bottom. And I need to replace the dx. So what does dx and du equal? Well, the derivative of u is 2 dx. So to replace the dx, I'll divide that 2 to the other side. So there's this 1 extra 1/2 out front. And now we have a 1/2 in front, and the integral now fits our arctangent rule. So arctangent said it's going to be 1 over a, which is root 3, arctangent of, in this case, u over a plus c. And I would go ahead and replace the u now with u, which is 2x. And this would be our antiderivative in terms of x. All right, so this one has a lot going on. If this is going to be an inverse trig function, it looks like it would have to be arcsecant because I have a function and a square root multiplied in the bottom, and also the order of the numbers in my square root. It's not a squared minus x squared, it's a function minus a constant. So the order is backwards. So I would look, if this is going to be arcsecant, what pieces do I have inside my square root? Well, for the 1 right here, well, that's my a squared. So obviously a is 1. This is my x squared. So similar to what we just did with arctangent, what am I squaring to get e to the 2x? You need to remember that e to the 2x is the same as e to the x quantity squared. Because when we multiply these exponents together, power to a power, we multiply. So e to the x squared is the same as e to the 2x. And what's nice is that means that our choice for u would have to be what's on the inside, which is e to the x. And I see e to the x's all over the place. I have an e to the x in the bottom and on the top. So let's just go through the substitution and see how that's going to actually help me. So in my denominator, that first e to the x can be replaced with u. My square root can be replaced with u squared minus 1. And then what's left over? Well, if u is e to the x, the derivative of u is e to the x dx, which is exactly what I have left to replace. So that whole thing there can be replaced with 1 du. And if we look, this is exactly our rule for arcsecant. So arcsecant said it's going to be 1 over a, so that's just 1. And I just put it there just to emphasize that it also has that 1 over a for its rule, just like arctangent. And the rest of it is arcsecant absolute value of u over a plus c. And again, I'll go ahead and replace the u with e to the x. So simply put, it's going to be arcsecant absolute value of e to the x plus c. That would be our antiderivative. All right, so this one's a little bit tougher, but let me walk through my thought process here. There's a couple of things I could definitely try. One problem is, if this were going to be any of the inverse trig functions, it would have to be arcsigned because I have a constant here and I'm being subtracted by x squared. The problem is, what do I have in my numerator? I have a 3x plus 2. If this was going to be an arcsecant, I need to have just a constant. I don't have, this doesn't require u substitution, so I have nothing to help me substitute out any of that. Okay, so what do we end up doing then? Well, think about what I just said. If I had only a constant, so if only this 2 were here, it would be an arcsign. Well, what other choices do I have? Well, what would happen if u were the inside of my square root? What if that was my u? Because one of the things we look for is letting u be the inside of our composition. And so the composition I'm looking at now is all of that right there. Well, the derivative of 4 minus x squared is a negative 2x. So I would love to have an x in my numerator, which I sort of do. I have a 3x, but it's being added to 2. And so that addition of 2 makes the substitution difficult. And if you can't see that right away, I'd encourage you to see what would happen if you tried to substitute in right now with u being 4 minus x squared. So for that to work, I would only want the 3x on top, not the plus 2. Well, what did I just say? It's going to be, u will be 4 minus x squared if I had just the 3x on top. It would end up being an arcsign if only the 2 was on top. So what do we need to do? We need to physically break this up. Since we have a single term in the denominator, just a giant square root, I can break it up and think of this as the square root of 4 minus x squared over the 3x. plus the 2 over the square root of 4 minus x squared dx. And now I have exactly what I was just saying. I have two different things being added together, so I can integrate them both separately. For the first one, this is going to be u substitution with 4 minus x squared being my u, and the derivative of u is negative 2x, which helps me get rid of the x that's in my numerator. The second one does not require u substitution. This is our arc sign rule. We just need to recognize that a is going to be 2. So for the first integral here, I'll do my u substitution. The 3 would get pulled out front. I have the square root of u in my denominator, and what do I have left? I have an x dx, so I have to divide that negative 2 to the other side. And if you need to pause the video and just check for yourself those substitutions, please do so. But that is the what my first integral would look like with the substitution. And let's go ahead and finish it up. So this would be negative 3 over 2, and we take the antiderivative of u to the negative 1/2 power. So we add 1 to the exponent, and we divide by the new exponent. That's our first fraction. And so our final answer for that piece, I'm not done with the second integral yet, but I have negative just 3, because the 2 times 1/2 will multiply to be 1, square root of u, which was 4 minus x squared. Plus, what happens to this integral here? Well, it's going to be 2 times the integral of 1 over the square root of 4 minus x squared, which will be arc sine of just x over a, which is 2. So I'll put that here, 2 arc sine of x over 2 plus c. And so this whole thing will be my antiderivative. But the key there was to break it up. One ended up being an inverse trig. The other one ended up being just a basic power rule when I used u substitution. All right, so for this one here, I always start off with these ones and ask myself, if this is going to be an inverse trig one, which one is it going to be? Well, it has to be arctangent because there's no square root in the denominator. All right, so if this is going to be arctangent, what do I need in the denominator? Well, I need a squared. So what am I squaring to get 1? Well, that's just 1 squared. And it needs to be plus x squared, or since it's not x squared, u squared. I'm going to have to use u substitution to figure out what am I squaring to get x to the 4th. And I need to recognize that x to the 4th can be thought of as x squared being squared. And so and I don't know why I just put a 1 there on top. There's an x on top. All right, so if I'm going to now make this an arctangent, I will need to use u substitution, and my u will be right there. My u would have to be x squared. And what I like about that choice, which works out really nicely for us, is that the derivative of x squared is 2x, which, what do I have in my numerator? I have an x. At first glance, especially right here, it looks like we're way off. You know, we have an x on top and an x to the 4th on the bottom. It looks like the derivative of x to the 4th would give me a 4x cubed. That would be the case if we were trying to make it a natural log and let u be the entire denominator. I would agree. If we tried to let u be 1 plus x to the 4th, that's not going to work. But with arctangent, we don't need an x or a u on the bottom. We need a u squared. So u would have to be x squared, and it works out great. So let's go ahead and run through the substitutions. So in my denominator, I get 1 squared plus u squared. I have an x dx on top, which is right there. So I'll have to divide that 2 to the other side when I substitute. And now this matches my arctangent rule. I'm going to get 1/2 times arctangent, which is 1 over a arctangent of u over a plus c. And while I'm at it, I'll go ahead and replace the u with the x squared. And that would be my antiderivative. All right, so for this one here, we have a quadratic on the bottom of our fraction, and that is it. So how are we going to go about this one here? Well, if you were to try something like u being x squared minus 4x plus 7, you're going to run into a lot of issues. That would be my strategy if I was going to try to make it into a natural log and having u on the bottom, because the derivative is 2x minus 4, and I only have a 1 on top, so that's not going to be my right choice. If this is going to be a trig function, I guess it could be arctangent, but arctangent needs a number squared plus a variable squared. The fact that I have an x squared and a negative 4x is going to make that process a little harder, but we can do it. What we have to do, though, is we have to recall how to complete the square, which is something we saw probably a while back. So we'll go ahead and refresh ourselves on how to complete the square. So I have x squared minus 4x, and I'm going to add something, and then I'll ultimately subtract that same something so that I'm adding 0 to my original problem. What do I add? Well, the magic formula for what to add is I'm trying to find the number so that this piece here I have underlined in red factors into a perfect square, meaning that when it factors, both parentheses are the same. That number that I'm going to add is half of the negative 4 squared. So half of negative 4 is negative 2. Negative 2 squared is 4. So if I'm going to add 4 there, I'm going to subtract 4 there. And so now if we were to factor this, x squared minus 4x plus 4, it factors to x minus 2, which is x minus 2 quantity squared. Over here, the other two constants will combine together. 7 minus 4 gives me plus 3. So how does that help me? Well, let me put that in there. My denominator can now be thought of, and I'm going to put the 3 first. It can be thought of as 3 plus x minus 2 quantity squared. And I would strongly encourage you to FOIL out x minus 2 squared, add it to 3, and what you're going to see is you will get the quadratic x squared minus 4x plus 7. These two things in the denominator are equivalent. But what's nice now is I can now use u substitution, and this fits our mold for arctangent perfectly. I would have to let u be what is being squared, which is x minus 2. But what's nice is the derivative of x minus 2 is just 1. So just to show all my steps, I'll go ahead and make my substitution. I get 1 over 3 plus u squared du. That is the arctangent of 1 over the square root of 3. 1 over a. Remember, this is a squared, so a is root 3. Arctangent of u over a plus c. And again, I'll go ahead and replace the u with the x minus 2. And that is our arctangent rule, needing to use the completing the square aspect to make the rule fit the mold. And this last example I wanted to put in here just to keep you honest, because not all of our antiderivatives that we look at are going to be inverse trig functions, nor am I going to tell you when they're going to pop up. You have to identify the rule. So on this one here, what you have to recognize, especially if I were to rewrite this, you can think of this fraction as arctangent of x times 1 over 1 plus x squared. And with u substitution, we're always looking for a choice for u, and that u's derivative also is in the problem. And hopefully you see that here, because it's the derivative of arctangent of x is exactly 1 over 1 plus x squared dx. That is our u substitution here, because again, if that is my u, this is the derivative of u, which is the pattern we're looking for when we do u substitution. And so when I substitute things out, the arctangent gets replaced with a u, and 1 over 1 plus x squared dx is exactly du. That is a very nice integral. And how do we take the antiderivative of this integral? This is just basic power rule. So it's going to be u squared over 2 plus c, and we ultimately turn it back. We get arctangent of x, quantity squared over 2 plus c. And so again, I just wanted to end this video with that example, just to emphasize the fact that They may not all be inverse trig functions, so ask yourself which trig function would it be, what would the appropriate u substitution have to be, and if it doesn't work out, maybe you need to be thinking about some of the other rules that we've seen in this chapter.